And this one. So this one is about Pelamis idea. We see the video and on Tuesday. So by the force of a wave, the structure is moving up and down in different motion. So by using that motion to convert that into piston motion, we can generate electricity. Now here is another idea. There are many ideas about wave utilization. Because the wave is usually effective on near the surface. There is no strong wave in deep water. So we need to focus on surface waves. And then by moving up and down, we can notice that the air or water can be used as a pump. So that is the idea. And then the location they tried is in San Francisco area, north of San Francisco area. Oh, there is one video. Let's see this video. Probably that has no sound. So I think it looks like a graphics rather than real system. So because of the wave, the top plate is moving up and down. And that motion, vertical motion, create motion inside the piston. So that can be used for generating electricity. So something is moving. This is the electricity. So electricity is collected and carried towards the land side to be utilized. So generation is from, okay. Okay. So there is the idea, then another one, next one is, it is also about a wave. This is named oyster wave energy converter. And that wave make the device moving front and backwards. And then there is a piston, seawater piston. And that piston makes the high pressure flow line is over. So some flow or oil can be pushed and down and up and down. And there is a hydroelectric power conversion plant is in the land side. Because usually the wave is strong near the shore and also only on the surface, it is possible to locate this kind of a device near the shore and also piping to the land side. Also, there is a video. Let's see.
Off the west coast of Lewis, in some of the wildest seas in the world, wave energy company Aquamarine Power has unveiled ambitious plans to develop what could become the world's first ever fully commercial wave energy farm. Using their oyster wave energy technology, they plan to capture the abundant energy in near-shore waves and transform it into clean, green electricity. The oyster wave energy devices will be located around half a kilometre from shore, in waters around 10 metres deep, and will be connected via subsea pipeline to an onshore hydroelectric generating plant. The oyster devices are simple, buoyant hinged flaps, which are attached to the seabed and pitch backwards and forwards in the near-shore waves. The machines are equipped with 2 vertical cylinders, each of which pumps high-pressure fresh water on both the forward and the backward stroke. This high-pressure water is then transported via a closed-loop subsea pipeline to an onshore power plant which uses tried and tested hydroelectric turbines to generate clean electricity on dry land. Each device is mounted on a piled foundation, drilled into the seabed by a jack-up barge. The buoyant flap can be towed out to the wave farm using a conventional workboat, and is then lowered down onto its foundation, a quick and simple process which can be reversed to allow easy removal as and when maintenance or replacement is required. Economies of scale can be achieved through connecting multiple devices via shared pipelines to a single generating station. This also helps even out the power fluctuations of the individual machines. The oyster devices have a certified design life of 20 years. Aquamarine Power's site on Lewis has the potential to become the world's largest wave energy farm. The company's received all required permits and consents from the Western Isles Council and the Scottish Government to install up to 50 devices along the coast at their site near Fivepenny Borv on the island's exposed west coast. Aquamarine Power believes wave energy presents a tremendous economic opportunity to local communities, Scotland and the UK, and it has the potential to make a major contribution to the world's green energy targets.
Okay, that's it. All right, so that is another idea. And then also there are many more ideas coming. So this one is Buldra, and it has a tank test in Trondheim. Trondheim is the second largest city in Norway. And also there is a 1/3 scale of floating rig. So it is tested on ocean, but there was a winter, so it is not working because of icing. Anyway, there is an owner. He may provide the money to invent and also test the idea. So the orange-like buoy is moving up and down. So by using that motion, we can generate electricity. Here is another one idea. So very similar to previous one. This one is moving up and down, right? Because this part is moving on buoy, right? So this one is also, the buoy looks, shape is different, but here the shape is similar, very similar. And then this buoy is moving up and down because of the wave motion. And then cable is attached. So by moving up and down, there is a motion of moving. So vertical motion, power is generated by the relative motion of the attachment inside the buoy. So inside the buoy, there is a generator. Okay. Somehow, so moving part and also fixed part should be combined so that the relative motion that is coming from wave movement, that is the main source of energy. Another idea is overtopping wave. The name is Wave Dragon. So there is a device with some size, and wave is coming and overtopping over the structure. Then the water is higher, and then it's going down into the ocean, return back. But here there is a turbine blade, so that energy is generated by using the overtopping water coming from the wave. So there's another idea. And the other idea is using air chamber. Right? They do a real test like this one, real construction near the beach. They are saying 500 kilowatt shoreline OWC, 2000 island in Scotland. So Scottish has a very good ideas. The other one was Scottish, right? Which one is Scottish? The video? Oh, this one. This one is on Scottish idea. And so wave is coming, then water is going up, water level is going up, then air inside the chamber is going outside. And reverse wave is going down, then water level is going down, the air is reverse way into the chamber. So there is an airflow that rotates the turbine, air turbine, and then we can generate electricity in this way. Okay, that is the end of the slide set. Any question? No? Then we can go on to Sangmin's lecture or third part of renewable energy.
Do you see my screen?
Yes.
Today's topic is ocean renewable energy. And current and summer energy part. As you can see this slide, compared to the traditional fossil energy, renewable energy, for example, solar and wind, energy density is very lower than traditional energy. So to generate efficient amount of electricity, the wide space is needed. This is the weak point for renewable energy. Compared to the solar and geothermal energy, wind and tidal energies, joule per cubic meter is bigger than these two kinds of renewable energy. This is the current energy. Current energy consists of surface current and deep ocean current. First of all, surface current is driven by wind. Due to the Ekman spiral effect, the current flow at 45 degrees to wind direction, and the surface current depth is 100 meters or above. And there are coastal currents. For example, crucial current. It is the very strong current. And deep ocean current is driven by water density and temperature gradient. This is the global conveyor belt. It could circulate the worldwide summer energy, and it is flow under the surface of the ocean. This is the figure for the surface current, not deep ocean current. in northern side, there are counterclockwise direction, and southern side, southern region, there are clockwise rotation flow. Some video. This is about how the ocean current works.
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths to chart a better understanding of ocean currents. Ocean currents are driven by a range of sources: the wind, tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean's surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis effect. The winds push the ocean beneath them into the same rotating gyres, and because water holds onto heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt, because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow, or if it stopped altogether. The only way we'll be able to forecast
next slide is about current energy. For the ocean current energy potential, ocean currents travel at speed is significantly slower than wind. But in terms of the energy density and kinetic energy, water is 800 times as dense as air. So 12 miles per hour ocean current would have energy output or density equal or greater to a 112 miles per hour wind. 1,000 of energy of Gulf Stream could satisfy 35% of Florida's energy needs. So in terms of the energy energy potential energy capacity. Ocean current energy is so huge amount of energy. This is the Korean Peninsula's ocean current. Around the South Korea, the main current stream is originated from the Taiwan and Philippines. That is the crucial current. Crucial current is mainly influence the Japan Peninsula and weakly influence to the Korean Peninsula. This is the crucial current. It is the west side of the North Pacific Ocean. This is the mainstream of crucial current. Let's see the crucial current video. This stream is a crucial current. It is influenced our Korean Peninsula. And this slide shows the submerged water turbine system. It is very.
We hear about strange things from distant places being washed up on our shores all the time, but how do they get there? Ocean currents.
It is very similar to the wind turbine system. It passes to the ocean floor. There are two types of submerged water turbines: horizontal axis and vertical axis. There are combined type generating system above the water, wind turbine system, and under the water, submerged water turbine system. Two kinds of system is combined to one system. This is the idea for the current generating system. The name is parachute type. This is the fasten the cable to ground and allowing the turbine to floating above. This is like kite farming, a series of kites that would rotate and open to the harness the current. This slide shows the global current power generation. Most of current power generation located in UK. The capacity is 300 300 kilowatt to 1 megawatt. And there in US there is a coastal river generating system. And in Canada there is a medium-sized current power generating system. In Japan, Nagasaki of Kyushu. This is the smallest peninsula of the Japan. There is a current generating system. The output is 2 megawatt, and diameter is 60 meter, and RPM is 10 to 16. It is very slow speed. Current generating system is a very similar structure of wind turbine system. There is generator and blade and pitch control system. By using the pitch control system, it could protect the blade or internal parts when the hurricane is coming. In USA, there are 3 major currents. This is Gulf Stream and Florida current, and this is the California current. There are loop current. It is rotate. Let's see the video.
The movements of surface water in the oceans. Their direction is influenced by many factors, including the rotation of the Earth, the size and shapes of the continents, the prevailing winds, and even water density. Ocean currents caused by prevailing winds are called drift currents. In the northern hemisphere, the circulation of the oceans is clockwise, and in the southern hemisphere, the currents are anti-clockwise. Currents originating from the polar regions carry cold water. There's the California current, the Peru or Humboldt current, the Labrador, Canaries, Benguela, the Antarctic circumpolar currents, and the Oyashio. Currents originating from the equatorial regions carry warm water. There's the Gulf Stream and North Atlantic Drift, the Brazil current, the North and South equatorial currents, and the Kuroshio. So perhaps it's not so surprising that many of the items that are washed ashore originate from far-off places, thousands of miles away.
This is the summer energy. Summer energy consists of Summer energy consists of 2 kinds of type. First, geothermal energy, and second, ocean thermal energy conversion. First of all, regarding the geothermal energy, the cold water is injected to the under the ground. That there are some very hot melting zone. And after touching the hot melting zone, and hot water is extracted to the heat changer, and it is turned to the steam and rotating turbine and generate the electricity. And regarding the ocean thermal energy, there are, compared to the geothermal energy, there are little thermal difference. So in terms of energy density, that is not so good. There are some video. Like these big figures, cold water is injected to the under the sea, and there is ammonia. Ammonia could condense and evaporated by changing the thermal energy. Hot water evaporate the ammonia. So eventually rotating the turbine and generate the electricity. Regarding the ocean thermal energy conversion, the top layer ocean received by solar heating, and bottom layer receive water from polar regions. So it can generate the natural temperature gradient, and by using the temperature gradient, it could generate the electricity. Then how to use the geothermal energy? If the source is under the 150 degree, then it could use the space heating and air conditioning and industrial process and drying and etc. like this. Then if the source is above the 150 degree, the simplest model is by one injection, cooling water, and extract the two pipe hot water. And by exchanging thermal energy, it could turn the turbine and it could generate the electricity. This is the binary cycle plant. This system is one cooling water is injected to the ground, and after exchange the thermal energy under the ground, and the hot water is extracted to the ground, and it could change the heat thermal energy. And by using the low boiling water fluid, it could convert it into the steam, and it could rotate the turbine, and after all, we can generate the electricity. This system is in the Casa Diablo, and it is located near the California. Yes. this is the lecture prepared. Is there any question?
No question?
Yeah.
Thank you.
Thank you very much.
Okay, then we may have a 5-minute break. After that, I can have my part of the lecture. Right? So I'll be back on 45. This is the last part of ocean renewable energy. Okay. We may finish or not. How many? 17 pages. Okay, let's see. Okay, so I will cover solar energy and biomass energy sources. So solar energy potential. So solar energy can be converted into electricity. So the amount is very big. All the energy sources on Earth is coming from the sun. Right? So it is about 300 watts per square meter per hour, something. And but only 0.02% of available solar energy can be replaced. All other energy sources. So once we can develop a technology that can convert solar energy into other energy. So energy conversion is the most important thing here. Only 0.02% of our solar energy can suffice all the energy requirement of humankind or Earth, not only human. Right? So energy radiated on the Earth in 1 hour is greater than all the energy of the world used in a year. So only a very big amount is coming. And right-hand side, incoming solar energy is, how can I read? It's petawatt. Right. And about half is absorbed by the land and oceans. And radiation is also big. And so only small portion is used by human and all the trees and other animals. Let's see the video.
Solar. Solar energy is the most abundant renewable energy source in the world. Solar energy systems employ technologies that convert the sun's heat or light to another form of energy for use. There are two categories of technologies that harness solar energy: solar photovoltaics and solar thermal. Solar photovoltaic, or PV, is a technology that converts sunlight into direct current electricity by using semiconductors. In contrast, solar thermal is a technology that utilizes the heat energy from the sun for heating or electricity production. Solar is a renewable resource and does not emit any greenhouse gases. However, efficiency and intermittency are issues. Since sunlight is dependent on location, season, and time of day, harnessing the energy from the sun is a challenge. That's solar.
Okay, that's the quick idea on solar energy. And so We usually use solar energy as a day lighting in the house and passive solar heating, because in Korea, most of the houses are facing toward the south direction to receive more solar light, sunshine, right? That can be a passive solar heating. And active solar heating is trying to capture those energy and use to another way, right? So we need to have a collection of solar energy by some ways of. In the middle of bottom, there is a special devices made of many of mirrors. And those mirrors are focusing into the one place and the center, top. So you can imagine that all the sunlight is concentrated in this single point. So it is a concentration of solar energy. Also, as you see from the video, that PV is to semiconductor which can convert solar light into electricity direct. Passive solar, sun's heating and materials that absorb that during the daytime. So this way, the facing toward the southbound of houses helps to receive more sunlight. Homes in Montana and California with a passive solar design, it's the home in the winter time and cools the home in the summer. They use this energy to cooling also. And passive solar design principles, we need to collect through windows or other ways and observe by dark colors. And there is a media to store the heat and circulation of the heat and control the surface. Right? So there is a diagram, 5 elements of passive solar design. Right? Also, we can see the video. No sound there. Okay.
Avoid long blocks that run north-south, as they make it harder to achieve a 6-star standard. Try to pick a block where you can have your living areas facing towards north on the block. By reducing the amount of wall area, you decrease the amount of inside space in contact with the walls, and this minimises the loss of heat and makes the home easier to heat and cool. Maximise the sun to living areas by putting them on the north side. It is best to face the utility rooms to the south. This will reduce the need to heat these rooms in winter and provide more natural light. You can see here how to divide your home up into zones to make best use of solar passive design. It's important you understand the movement of the sun in relation to your block selection and your home design. You can see here the rotation of the summer sun. In summer, the sun is higher in the sky. By designing your home correctly, you can make sure the home is shaded in summer with eaves and other shading devices. From this view, you can see that the sun is not streaming into the north side windows, keeping the home cool on summer days. In winter, the sun is lower in the sky. This means that the sun can penetrate through the windows to the interior of the home, creating heat gain and reducing the need for artificial heating. In this view, you can see the sun penetrating into the living area and warming the home. Once you have correct block selection and home orientation, it's important to shade correctly so that in winter you can get heat gain from the sun and in summer you are protected from the sun's rays. A simple way of achieving this is to ensure that your home has eaves or other shading devices. Pergolas can be used to keep out the summer sun. Remember to install at correct angles so that light can penetrate into the living rooms. Vertical and horizontal architectural features act as shading devices to keep out the summer sun. You can also use roller shutters or external awnings. Covered open spaces, commonly known as alfresco areas, should be placed on the south side of the house. This leaves the north side open to receive the winter sun. A covered area on the north side means sunlight cannot penetrate into the house, reducing warmth and natural light. You can still have private outdoor open space to the north of the home, but it should only have temporary shading which can be withdrawn in the wintertime. The example here includes a pergola on which a deciduous vine can be grown, which provides shade in summer, but allows the winter sun in when the leaves fall off. And again here, the uncovered open space allows the sun to penetrate into the living areas. Thermal mass is the ability to absorb, store and re-release heat. Thermal mass is heavyweight construction such as concrete or brick, but needs to be used on the interior to work as thermal mass. The advantage of having thermal mass in your home is that it moderates the indoor temperature in both winter and summer, as seen over the next few simulations. The winter sun shines down into the living rooms. The heat is stored in the thermal mass. As the air inside the house cools during the night, the heat in the thermal mass gets re-released back into the room and helps to maintain the internal temperature, requiring less heating. In this fly-through of the home, you can see how the winter sun is penetrating into the living room from the north side and how the concrete floor slab is storing that heat to be released at night. You can also see the living room is fully lit from the winter sun, requiring no artificial lighting in the daytime. The summer sun is higher in the sky, so with correctly sized and proportioned eaves and other shading devices, you can keep your home cooler by keeping the heat out. During the day, as the air inside the house warms up, it is absorbed by the slab, which is cooler because it is in contact with the cooler earth. This keeps the internal temperature cooler. At night, as the air inside the house cools, the heat from the slab moves back into the room. It's important then to have breezeways which can be used to cool the house by opening windows or doors. Looking at the interior of the home in summer, you can see that occupants are shaded from the harsh sun. In conjunction with the use of thermal mass, it's important that your home has good breezeway design as shown in this fly-through. You can also reduce the energy required to heat or cool your home by creating an airlock at the entry of your home. This creates a buffer from the internal and external environments and reduces the amount of heat loss during winter.
Okay. That is coming from Department of Planning and Community Development. Probably, I guess, it's in Los Angeles area or California area. So it is reverse way. Home is facing for northbound, rather than in South Korea, we are trying to face houses toward the southbound. Because I guess Southern California, there are too much sunshine. So usually the houses are facing for northbound. Oh, that is interesting to me. Probably, Adib, you have a similar situation in Bangladesh, so that you need to have a probably north face. Is it right? How is your housing there? Adib, are you listening to me?
Yes, sir.
So what is the usual direction of houses in your country?
It's usually either north facing or south facing.
North, south, no? North or south? Because in Korea, the houses are usually facing toward the south to receive more sunshine. But in this video, they are saying they trying to face the houses for north direction, to facing the north direction, to protect the house from the hard sunshine from in summertime, but also want to receive sunshine in wintertime. That is better for north-facing houses in this case. So my question is, how about your country? Because your country is very hot region there, what is the usual direction for housing?
Yeah, usually most of the houses are apartment buildings, and usually they are either north facing or south facing.
North or south? Okay.
Yeah.
Both, you are saying both. Okay.
Yeah, so for example, I think my apartment is south facing, but the other house, the other side, they're north facing.
You see. So in your country, there is no big difference between south facing and north facing in terms of sunshine, right?
I think the south has more sunlight.
Right.
But previously, I lived in a north-facing house, and we didn't have much sunshine at that time. Now we have more.
Okay. Thank you. Let's go ahead. Then next one is about active solar heating. So they trying to utilize the solar energy by using pumps. So dark color plate that absorb heat and air or liquid flows are used to control actively control the heating circulation. For flat plate collector, so small tubes run through the box, and then anti-freezer or water is used to contain the energy, it stores the energy, and then transfer heat directly to the interior space to storage for later use. Right? So there is, you see that plate to collect solar energy there, usually on the roof here in the picture too. And photovoltaic, that is converting solar energy into electricity. PV, photovoltaic system convert sunlight directly into electricity. Also known as solar cells, PV systems are already an important part. And small calculators, where is it? This one, probably, I don't know. And wristwatches also used for the everyday life. Oh, there's also video there.
Starting out with any new project management software usually feels something like this. Where do you even...
The Earth intercepts a lot of solar power, 173,000 terawatts. That's 10,000 times more power than the planet's population uses. So is it possible that one day the world could be completely reliant on solar energy? To answer that question, we first need to examine how solar panels convert solar energy to electrical energy. Solar panels are made up of smaller units called solar cells. The most common solar cells are made from silicon, a semiconductor that is the second most abundant element on Earth. In a solar cell, crystalline silicon is sandwiched between conductive layers. Each silicon atom is connected to its neighbors by 4 strong bonds, which keep the electrons in place so no current can flow. Here's the key. A silicon solar cell uses 2 different layers of silicon. An N-type silicon has extra electrons, and P-type silicon has extra spaces for electrons, called holes. Where the 2 types of silicon meet, electrons can wander across the p-n junction, leaving a positive charge on one side and creating negative charge on the other. You can think of light as the flow of tiny particles called photons shooting out from the sun. When one of these photons strikes the silicon cell with enough energy, it can knock an electron from its bond, leaving a hole. The negatively charged electron and location of the positively charged hole are now free to move around. But because of the electric field at the p-n junction, they'll only go one way. The electron is drawn to the n side, while the hole is drawn to the p side. The mobile electrons are collected by thin metal fingers at the top of the cell. From there, they flow through an external circuit, doing electrical work like powering a light bulb, before returning through the conductive aluminum sheet on the back. Each silicon cell only puts out half a volt, but you can string them together in modules to get more power. 12 photovoltaic cells are enough to charge a cell phone, while it takes many modules to power an entire house. Electrons are the only moving parts in a solar cell, and they all go back where they came from. There's nothing to get worn out or used up, so solar cells can last for decades. So what's stopping us from being completely reliant on solar power? There are political factors at play, not to mention businesses that lobby to maintain the status quo. But for now, let's focus on the physical and logistical challenges. And the most obvious of those is that solar energy is unevenly distributed across the planet. Some areas are sunnier than others. It's also inconsistent. Less solar energy is available on cloudy days or at night. So a total reliance would require efficient ways to get electricity from sunny spots to cloudy ones, and effective storage of energy. The efficiency of the cell itself is a challenge too. If sunlight is reflected instead of absorbed, or if dislodged electrons fall back into a hole before going through the circuit, that photon's energy is lost. The most efficient solar cell yet still only converts 46% of the available sunlight to electricity, and most commercial systems are currently 15 to 20% efficient. In spite of these limitations, it actually would be possible to power the entire world with today's solar technology. We'd need the funding to build the infrastructure and a good deal of space. Estimates range from tens to hundreds of thousands of square miles. Which seems like a lot, but the Sahara Desert alone is over 3 million square miles in area. Meanwhile, solar cells are getting better, cheaper, and are competing with electricity from the grid. And innovations like floating solar farms may change the landscape entirely. Thought experiments aside, there's the fact that over 1 billion people don't have access to a reliable electric grid, especially in developing countries, many of which are sunny. So in places like that, solar energy is already much cheaper and safer than available alternatives like kerosene. For, say, Finland or Seattle, though, effective solar energy may still be a little way off.
All right. Okay, so it's about solar energy. Let me see, and then concentration of solar power. So mirrors direct sunlight on the one point, and then water is turned into steam and boiled or hot water, and then steam generated to make a turbine to rotate. And concentrating solar power or CSP plants use different kind of mirror configuration. So here is a mirror configuration to make a high temperature heating. And so, but the disadvantages here, as the video says, once the mirrors, curved mirrors are not cheap, so it's expensive. And also there should be a maintenance cost of piping and cleaning of the mirror surface. And also to get enough sunlight, you need to have a lot of space. That is the most critical disadvantage in these days, especially in Korea. The space is not enough, so that many people are complaining about this, using solar panels near my home. Okay, then there is a biomass. We can stop here. And we can continue on this evening. All right? Any question? No? Then see you on evening time. Bye now.